All right, folks, welcome back. Let's go ahead and let's pick up where we left off with yesterday. And I would like to today try to finish up with the discussion of the mole ratio and try to get to the two conversion, couple conversions that I want to do with you involving masses and moles here, and then hopefully volumes and moles of the substances involved in a chemical reaction. So I'd like to get those two calculations done today if we can. But let's go ahead and let's take a look at where we left off with yesterday. I want to try to finish up with the Pogel activity that we started yesterday as well. So have that in front of you. So go ahead and pause the video right now if you don't have it, and go get it. And then let's use that to continue the discussion today. Okay. All right. So we talked yesterday about how the coefficients of a balanced equation also gives us information about the number of moles involved in the chemical reaction. Okay. And remember, from what we learned back in chapter 10, the unit of mole, this unit mole here indicates a certain number of objects, and it indicates this many objects. And the objects that we are studying when we talk about chemistry then are the atoms, the molecules, so the particles themselves. Okay? And so the unit mole indicates that. So from the balanced equation, the coefficients themselves provide us with that information. The reason for that, and the reason why we're going to work with the unit mole then, is that even though we can interpret the chemical equation at the molecular level and at the atomic level, that's not very practical for us. I mean, when we're trying to run a reaction, we saw this with the Pogel activity, we can calculate for the number of atoms that are involved in a particular reaction. We can count them. We can use the coefficients to do that. We can determine then the number of molecules that are involved in a chemical reaction as well. Okay, and we can use the coefficients to do those very simple calculations. And we saw that with the Pogel activity. But it's not something that we can do. We can't run a chemical reaction with 600 molecules or 600 particles. That's not possible. However, when we start talking about this many particles here, which is Avogadro's number of particles, that we can do. Now, we can't actually measure out, we can't actually count out this many particles. That would not be practical. And I pointed out to you that if you tried to run reaction this many times, it would take a very, very long time in order for you to get that done. However, we also cannot count out this many particles either. It's not possible for us to go in there and individually pick out this many Avogadro's number of particles. Again, that would take us forever, and we can't isolate individual particles. Okay? And so what we need to be able to do then is we need to be able to, at some point, and that's why I want to get to today, at some point we should be able to take this here, this many number of particles, and figure out then the mass equivalent to it. So because we can weigh that out, okay, or the volume equivalent to this many particles. Okay, and so remember, this is a counted quantity, so we can count out this many. That's not practical. It actually is not possible. It would take too long. But we can measure out a mass that's equal to this, which then would be equal to 1 mole. So the conversion we want to be able to do is from moles to mass and moles to volume, okay? Because we can count this, we can weigh this out, and we can measure this volume out as well. Okay, so the goal for today is to be able to convert between this unit here, and these two units here, okay, in the context of a chemical reaction. Okay, and we can do that if we understand then what information is given to us from the chemical equation. Okay, so from a chemical equation, remember, and make sure you keep this in mind, a balanced chemical equation, when no number is written, it's understood to be 1. Okay, so from a balanced chemical equation, we can obtain information about the number of atoms involved. We can obtain information about the number of particles involved, but we can also obtain information about the number of moles involved as well. Okay, and so that's where we left off with yesterday. So we were to interpret this equation in terms of number of moles with this many particles again. We would say then that we start out with 1 mole of nitrogen. Okay, and to that 1 mole of nitrogen, we will add in 3 moles of hydrogen. And if we combine those together, we should expect then to form 2 moles of ammonia. Okay. All right, so with that said then, if you take a look at this, we total up the number of moles. So we have a total of 4 moles on the left, but we only have 2 moles on the right. Okay, and so with that said, the number of moles on either side do not equal. Okay, so again, the number of the number of atoms that have to be equal, but not necessarily the number of moles. Okay, so let's make sure you keep that in mind. So that's where we left off with yesterday. That's what we were talking about yesterday. Okay, and so let's go ahead then and let's take a look at okay, number 7 in your POGIL activity. So let's go and do that. All right, so where we left off with yesterday is we talked about this, and so I'm going to go ahead and write the equation up here again for you. Let's go ahead and write the equation up here. Okay, we have then 1 nitrogen, and I'm sorry, it's why am I doing that? Let me go ahead and erase this here. Okay. And so with that said, then we are taking a look at this equation here again. So we're going to look at this equation here, and we're going to use this to solve for some problems. Okay, now. You can use proportions, but what I would suggest you here is do a simple conversion. Okay, so let's go ahead then. Let's consider what we have here. Okay, and so we were told then, we know this, folks, in a chemical reaction, we want to compare then how many moles of nitrogen is needed to make 10 moles of ammonia. We know this. We know then that if we have 1 mole, and this is from the previous example, we have 1 mole of nitrogen. We know then that we will make, and that will be equal to, and that's kind of a long equal sign there, but it tells us then from the balance equation that if we start out with 1 mole of nitrogen, we will produce 2 moles of ammonia. Okay, that is given to us. That is what we expect to happen, and we know that that will be true. Okay, and I'm sorry, moles here. Let me go ahead and erase this real quickly. Sorry. Okay. We should expect then to form then 2 moles of ammonia. We know that that has to be true. So for example here, if I were to ask you, if you know that to be true, if we reduce this amount to half a mole of nitrogen, we only start out with half a mole of nitrogen, I think it's fairly intuitive that you know then that we only form, that this has to change as well. We only produce then 1 mole. We produce half. If we start out with half as much nitrogen, we should produce then half as much ammonia. Okay? And conversely, if we double the amount of nitrogen that we start out here, we should expect then that this amount to be increased, and it should increase by a factor of 2. So we should end up with 4 moles of ammonia here. What basically you just did was, folks, you just did a conversion in your head. Okay, and so what you need to make sure you understand then from what we did in chapter 10 and what we did in chapter 3, that in the process of doing conversions here, what we're doing is we're comparing amounts. That means that if we change the amount on one side, we expect then that the amount should change on the other side as well of this equality. Okay? All right, so let's do this then not as a proportion. And I don't want you to do it that way because it's not going to help you as we move forward. But let's do this as a conversion. And so remember, with the conversion, 3 questions you have to ask yourself then is, what do you start out with? What is it that you start out with? Okay. Second question is, what do you want to end up with? Okay. What is the ending unit? And then ending amount. Okay. And then what are the conversion factors that you need? And this is what we have been doing since chapter 3. Okay. All right, so taking a look at this problem here, so I'm going to go ahead and erase this here really quickly. So take a look at this first problem here. What do we start out with? And let's go ahead and label this here. We start out with, we are told then that we have 10 moles of ammonia. That's the amount that we have to start out with. They identify that for us. Okay. What they want us to solve for then is moles of nitrogen. So this is what we are starting with. So this is the start. Okay. This is what we want to end up with. This is our end, and there is our conversion factor. Okay, so here is our conversion factor here. And we'll have to set it up now, remember, in order to get that done. So let's go ahead then, and let's work out this problem. So we start out then with 10 moles. That means then they're asking us if we produce 10 moles of ammonia. So we're kind of working backwards here. How many moles of nitrogen did we start out with? The idea here is this, folks. You understood then if we doubled this or we took half of this, that this would change. Okay. The question now is, what if I had 6 moles here? Let's say we tripled the amount of ammonia that's produced here. could you predict how much we started out with? And obviously the answer is yes. If we triple them out here, we would have to triple them out here. So that means that we needed to start out with 3 moles of nitrogen. That's what we're doing here. They're telling us that if we start out with 10 moles, that if we produce 10 moles of ammonia, how many moles of nitrogen did we start out with? And so again, I think you can probably do this in your head, but let's just work this out as a conversion problem. Okay, so with that said, then this is the quantity that they give us. So the starting amount then is the amount that they give you. The end amount is what they want you to solve for. If you want to think about it in that way, so let's go ahead and let me write that way. So this is what is given. So this is the given amount. So I think most of you probably recognize that. This is what we are solving for. This is what we were solving for. Okay, this is what we're solving for, and that's our conversion factor. So that's what you're going to be doing as you read the problem. That's what you're going to identify. Okay, all right. So we are given 10 moles of ammonia. We want to solve for the moles of nitrogen. Let's go and plug this in. Okay, how do we plug this in? We plug this in so that this unit cancels out, which means then it's going to be 1 mole of nitrogen on top and 2 moles of ammonia on the bottom. That cancels out then. And therefore, then we plug this in, and hopefully, I think everyone here recognized that the answer is going to be 5 moles of nitrogen. Okay. All right. So that's what you want to do. You want to work out these problems as conversions. So let's go ahead and let's take a look at the second one here. Okay. So let's go ahead and identify what what we're starting out and what we are given. Okay. So this time then, what we're given and then what we're solving for, that is what we want to end up with. This time, this is what we were given. We're given 9 moles of hydrogen. So that is the start. That's what we're starting with. Okay, so that's the given. They want us to solve for moles of ammonia. Okay, that's what we want to end up with. Okay, and so with our conversion factor then, and I'm just going to write this as CF. Okay, our conversion factor then we can get that from the balance equation here, because this time we're comparing hydrogen and ammonia. Okay, so therefore then we know then with, oops, sorry, let me go ahead and change this real quickly. Okay, and to solve the problem. Okay. We know then that for this particular problem, we have then 3 moles of hydrogen is equivalent to 2 moles of ammonia. So that's what we're going to use to solve for this one. Okay. So I think, folks, this is all from chapter 10. This is something that I think is very familiar. These conversions should be fairly straightforward, but let's just quickly go through this. So let's go ahead and write this down then and solve for it really quickly. We start out then with 9 moles, okay, of hydrogen, and we are solving for moles of ammonia. Okay, so plugging in our conversion factor here, then it's going to be 2/3. Hopefully everyone recognizes that. It's going to be 2 moles of ammonia over 3 moles of hydrogen. Why do we do that? Unit of hydrogen cancels out. And so when you plug that in, you should end up with an answer that is 6 moles of ammonia. Okay, so hopefully you got that done right. Okay. All right, then finally, let's go ahead and quickly do the last one here, and real quick, let's identify what we're given. This time we start out with 7.41 moles of nitrogen. That's what they give us, so that's what we start out with here. Okay, we are asked to solve for moles of hydrogen because that's what we were solving for. That's what we're going to end up with. Okay, and so with our conversion factor, let's go ahead and write that down. Okay, with our conversion factor, then it's going to compare hydrogen to nitrogen, which is going to be then these two. So for every 1 mole of nitrogen, okay, we have 3 moles of hydrogen. Okay, so this is the conversion. That's what we're going to use to set up our conversion factor. Okay, all right, so let's go ahead then and write out what we have. We have 7.41 moles of nitrogen, and we are solving for moles of hydrogen. Okay, plugging in our conversion factor, then hopefully you see it's going to be 3/1, 3 moles of hydrogen, 1 mole of nitrogen, sorry. Okay. Why? Because that cancels out here. And so if you plug that in, you get your answer then as being 22.2 moles, and hopefully you got that, folks, moles of hydrogen. Okay. So make sure you can do these calculations, but make sure you also understand what it means in the context of a chemical reaction. Okay. So let's real quick, let me make sure you understand this. So I already explained this to you here. What we're saying chemically here is that what the question's asking you then is, if 10 moles of ammonia is produced, how many moles of nitrogen did we start out with? And that's what we solve for here. That's what this answer. That's the answer to that question. Okay, so the question then is, if you produce 10 moles of ammonia, how many moles of nitrogen did we need to start out with? 5 moles. So you can imagine this in the chemical context. If you were asked to produce, if your supervisor, if your advisor, when you get up to college and you're doing research, asks you produce for the lab 10 moles of ammonia, you have to go back and you have to calculate then for this. Okay, you have to ask yourself then, well, how much nitrogen do I need to start out with if I'm going to carry out this reaction here? If I'm going to run this reaction, and this is the recipe, this is the instruction that I'm going to use to make this ammonia. If my supervisor wants me to make 10 moles of ammonia, I need to then make sure that I measure out 5 moles of nitrogen. Now, you still have to calculate and determine how much hydrogen you have, but then you've already, at this point here, figured out how much nitrogen you need to start out with. And that's what this particular calculation gives us. That's what it allows us to do. Using a cooking analogy, let's imagine this. If the recipe that you use calls for, tells you that you can produce 12 cookies using a certain number, 4 cups of flour, okay, 4 cups of flour, but you wanted to make more cookies, okay, then what you have to do is you have to use that and go back and calculate then for how much flour you need. You change the amount of flour to produce more cookies, and that's what we have here. We want to produce more ammonia than what we have here. Here we only have 2 moles. We want to produce 10 moles of ammonia. We have to use more nitrogen. Okay. And so what you need to be able to do is you need to be able to interpret what these calculations mean in the chemical context. I think doing the calculations should be simple. I think the calculations are very simple calculations. Moving forward, what you need to be able to do is you need to be able to interpret what it means. Okay. All right. So with that said, then the question we need to answer, and it's going to be an important question then, is can we actually measure out 5 moles of nitrogen? Is there a measuring tool? Is there a device that we can use that allows us to measure out 5 moles of nitrogen? And the answer there is no. We don't have a cup. We don't have a balance. There is no digital measuring device that allows us to measure out moles of nitrogen in order to produce this many moles of ammonia. Okay. So what are we supposed to do then? In this instance, what are we supposed to do in order to get that done? Okay. Well, what we need to be able to do is we need to be able to find and calculate for the masses that are involved, because we can measure out masses. Okay? We can measure out mass using a triple beam balance. We can use a digital balance to measure out masses. Okay? So what we need to be able to do is we need to be able to figure out a way that we can take the coefficients, okay, the coefficients from the balance equation. Can we take these coefficients from the balance equation and find mass from them? Well, first of all, the coefficients do not give us the amount of each one of those reactant products for the masses. Okay, so for the balance equation that we talked about already, so let's go ahead and take a look at this balance equation here. The coefficients here, folks, understand this, the coefficients here, the 1, the 3, and the 2, do not tell us anything about masses. So the coefficients here do not give us information. So this is not 1 gram of nitrogen combined with 3 grams of hydrogen to produce 2 grams of ammonia. That's not what the coefficients give us. The coefficients give us the number of atoms, the number of molecules, and the moles, but it does not say anything directly about the mass. And so it does not relate. So the coefficients do not relate. And so you got to make sure you keep this in mind. This is going to be important. They do not relate the amounts of masses directly. That's not the information that we get from this directly. They do not relate the amounts of, and I should say this amount in terms of masses, okay? Okay, in terms of the mass of each reactant and product directly, okay? However, if we recall, and if we remember from chapter 10, okay, there is a relationship between moles and mass here, okay? And so we remember then that that relationship is the molar mass. And if we remember this molar mass, okay, if we remember how to use it, and remember what it is, we can then obtain information about masses here. Now, again, we can't get it directly, but we can calculate for it. Okay, so what you need to make sure you keep in mind then is that when we find the masses of the reactants and products, okay, when the reactants and products, okay, we have to be able to calculate for it. We have to be able to calculate for these masses here. And so to get these masses here, okay, we have to do a simple calculation. We have to calculate for these, okay? We cannot get it directly. However, at the end, what you will notice is that based on the law of conservation of mass, the mass of reactants, the total mass of reactants, and the total mass of product will be exactly the same. That will be very useful as we go through and we calculate for these masses here. Okay? All right, so let's go ahead then and let's try this. Okay? Let me go ahead and let's pull up the what we have here with the POGIL activity. And so this chart here, remember, this chart we obtained from, this is a problem that we did. We obtained this, this was from number 4 in your, from the POGIL activity. So this is, we filled out this chart from question number 4. Okay, so this is from question number 4. And so I just went ahead and reposted here. And I'm running low on time here, so we'll finish this up on Monday, but I just want to preview what we'll be talking about on Monday. In number 4 here, and make sure you take a look at that. What we did then is we used this balance equation, and then we talked about then if we had this many particles, so we have Avogadro's number of nitrogen, we would produce 3 times that. We would need 3 times the amount Avogadro's number of hydrogen to produce 2 times the amount of ammonia here. Okay, so basically we took then Avogadro's number here, tripled it here, and doubled it here to get our 1:3:2 ratio, which represents the ratio of the balance equation. Okay, and then we saw then that with moles here, this represented if we have Avogadro's number here, that's exactly 1 mole. This is 3 times Avogadro's number, so we'd have 3 moles here, and then 2 moles here. So that's where we got the mole ratios here from. That's our mole ratio. Okay. So the question we need to ask, and I would like you to consider then, and I want you to write this down, okay? What is 1 mole of nitrogen equivalent to? So I want you to finish up here. I want you to do this calculation for me, okay? What's the equivalent amount in grams of nitrogen if you have 1 mole of nitrogen? What's the equivalent mole of hydrogen, equivalent grams of hydrogen, okay, if we have 3 moles of hydrogen? And then finally calculate then for the mass of ammonia, okay, if we start out with 2 moles of ammonia. So I want you to do this calculation here, and this calculation here. So do those 3 calculations, write them out on your paper, okay, and then submit it. And then what we'll do then is on Monday, we'll go ahead and do this. We'll go ahead and work this one out together. Okay, so get that done, folks. Make sure you post it, and then we'll use this to start out the discussion of the mole to mass conversion here on Monday. Okay, have a good weekend, folks. If you have any questions, please make sure you stop by after school today and get your questions answered. Okay, and if not, I will see you on Monday. Okay, have a good weekend.